Hi, my name is Oktay. Welcome to today's video about high-temperature superconductors. This is a picture of a magnet floating over a superconductor that is at a temperature below the critical temperature. This effect is called the Meissner-Ochsenfeld effect. This is an explanation of the Meissner-Ochsenfeld effect at the right. This picture at the right shows you the situation below the critical temperature. Then you get an expulsion of a magnetic field in a superconductor, and that makes the magnet float. This effect was discovered by Walter Meissner and Robert Ochsenfeld in 1933. This is the gentleman who discovered superconductivity, Heike Kamerlingh-Onnes, in 1911. In the middle, that's his original diagram. And he found that mercury became superconductive at a temperature below 4.2 Kelvin. For this discovery, Heike Kamerlingh-Onnes won the Nobel Prize in Physics in 1913. He was also the first person who produced liquid helium, which led to the discovery of superfluid helium-4 at a temperature below 2.2 Kelvin in 1937 by Kapitsa, L, and Meissner. That's the picture at the right. Superfluid helium has no viscosity. It automatically creeps over every wall until all these heights are the same. This is the BCS theory, Bardeen-Cooper-Schrieffer theory. It explains superconductivity. For this theory, the Nobel Prize in Physics was given in 1972 to John Bardeen, Leon Cooper, and John Robert Schrieffer. You got a pair of electrons that are bound by phonons, which are quantized sound waves. Superconductivity is a phenomenon at low temperature because then the movement of the atoms is very low. A Cooper pair of electrons can travel through the structure without loss of energy. However, the BCS theory did not predict high-temperature superconductors. This was the first high-temperature superconductor, Yttrium, Barium, copper oxide. For this discovery in 1987, the Nobel Prize in Physics was given to Georg Bernoulli and Carl Müller. High-temperature superconductor means its critical temperature is above 77 Kelvin, which is the boiling point of liquid nitrogen. This is a picture of the structure of yttrium, barium, copper oxide. The X in this formula is important. This kind of structure is called a perovskite structure with the general formula AbX3. You got CuO2 ribbons and CuO4 planes. But it's a defective variant of the perovskite structure. And what's important is 2/9 of the oxygen positions are unoccupied. This is a non-stoichiometric compound. And this is important for its property as a high-temperature superconductor. This is a timeline of the discovery of different superconducting materials. Some elements are superconductors, some alloys. Then there's this group of cuprates, fullerenes, borides, iron compounds, and polyhydrides. Now, y-axis is the critical temperature, and x-axis is the time year of discovery. This is room temperature. And the holy grail is to find a material which is not too expensive and has a critical temperature above room temperature. That's very important. And you can see at the top right some compounds, some superconductors only at high pressure. This is a periodic table of superconducting elements. Yellow is at ambient pressure and blue is at high pressure. For example, mercury at 4 Kelvin, bismuth at high pressures at 8 Kelvin, sulfur at 17 Kelvin. There are two types of superconductors, type 1 and type 2. Coherence length is symbolized by this Greek letter Xi, and lambda is the magnetic field penetration depth. In this picture, it's in red color. Superconducting phase is in light blue in this picture. At the left, if Xi is much bigger than lambda, then you get a little penetration field. These are the type 1 superconductors. Their superconductivity is abruptly destroyed by a strong magnetic field. Examples are these elements, aluminium, lead, mercury. Then there's type 2 superconductors, where lambda is much bigger than Xi. Now you have this situation. You have an intermediate phase of normal conducting and superconducting at intermediate temperatures and intermediate magnetic fields. The majority of the high temperature superconductors are type 2 superconductors. This is a picture of the Buckminsterfullerene C60 soccer ball molecule. It was produced in 1984 by laser vaporization of carbon in a helium beam. For this compound, the Nobel Prize in Chemistry was given in 1996 to Harold Kroto, Robert Curl, and Richard Small. This compound is named after Richard Buckminster Fuller. He was an American architect, inventor, and futurist. Fullerides are anions of the C60 molecule, and some tri-anion compounds are superconductors. The sodium fulleride is not among them because it has a different structure. But potassium fulleride is a superconductor with a critical temperature at 18 Kelvin, rubidium fulleride at 28 Kelvin, and cesium fulleride is also a superconductor with a critical temperature at 40 Kelvin, but only at high pressures. This is BISCO, bismuth, strontium, calcium, copper oxide. And this was the first high-temperature superconductor that contained no rare earth element. And it was also the first which was used for superconducting wires. It was discovered in 1988. There's a numbering system, bismuth 2223. These digits give you the number of the cations. For example, bismuth 2223 is bismuth 2, strontium 2, calcium 2, copper 3. And again, this X is important. Critical temperature of BISCO is at 108 Kelvin, which is above the boiling point of liquid nitrogen at 77 Kelvin. This is another class of superconductors, that's the iron-based superconductors. They were discovered in 2006. These compounds are iron pnictides or oxypnictides. And they have a cost advantage because they are made of very abundant elements. Their critical temperature is between 25 to 56 Kelvin. And in this picture, you can see there are layers of ions, are red, and of the pnictides. For example, this arsenic. Doping it with element praseodymium stabilizes this structure. There's another compound that's iron selenide. Was put on as a layer on a strontium titanate. This is called epitaxy. And this compound had a critical temperature of 105 Kelvin, which is above that of liquid nitrogen. There's another group of compounds, polyhydrides, also called superhydrides. These are hydrogen-rich compounds that only exist at high pressures. For example, sodium heptahydride, which contains H3- anions. And some of these compounds are superconductors. For example, lanthanum decahydride, LaH10, has a critical temperature of 250 Kelvin, which is just minus 23 degrees Celsius, but only at 170 gigapascal, very high pressure. And these compounds are also interesting as a potential storage of hydrogen. So most elements in the periodic table are metals. So this means there are many combinations for potential compounds. And this is a good problem for computational chemistry. You can predict the properties of different compounds. And there's this group of ternary polyhydrides, for example, Li2MgH16. This compound could have a critical temperature of 200 degrees Celsius. Again, you have, in this case, you have even more possible combinations of elements. And this problem is a very good problem for a neuronal network to solve. It can predict the properties of these compounds. These are two methods to study superconductivity. At the left, that's STM, scanning tunneling microscopy. It allows you to observe single atoms on a surface. And at the right, that's ARPES, angle-resolved photoelectron spectroscopy. It's based on the photoelectric effect. Albert Einstein was able to explain the photoelectric effect, and for that he got the Nobel Prize in Physics in 1921. This is one of the applications of superconductors. It's for the superconducting quantum computing system device. This is a picture of a 4 qubits IBM device with quantum buses and 4 readout resonators. The quantum computer is by far the superior computer compared to normal computers. That's because of the special properties of the qubit compared to the normal bit. This is a cutaway of a superconducting magnet. It's a picture from the Nicolaus Copernicus University in Torun in Poland. This is a picture of a superconducting magnet. The coins show the constant magnetic field. In a superconductor, you have no resistance. So once the magnetic field is built up, you don't have energy consumption anymore. This is another application of superconductors. It's for MRI, magnetic resonance imaging. This is a real-time picture or a movie of a beating heart. This is a picture of the maglev train in Shanghai. It is very impressive. It can reach a top speed of 430 kilometers per hour. And maglev trains are another potential application for superconductors. You can check on YouTube, there are great videos. This route in Shanghai has a section which is next to a motorway. And the train makes the fast cars in the motorway look like they're standing. It's very impressive. This is how this works. Propulsion process in a maglev train with electrodynamic suspension. The magnetic field in the tracks is changing regularly, and this gives the train its speed. This is a picture of the Wendelstein 7X experimental stellarator. Stellarator is a concept to make hydrogen fusion work. This is located in Greifswald in Germany. This is a picture of its structure. They use superconducting magnets at minus 270 degrees Celsius, which is 3 Kelvin. Each of these magnets has a mass of 6 tons to hold the plasma in the vacuum chamber. And there are 20 additional magnets. They help adjust the magnetic field in the vacuum plasma chamber. The chamber is made of high temperature resistant metal and graphite. its size is 30 meters. You can see here, for comparison, size of a human. The mass of this construction is 750 tons. The costs are 1.06 billion euros over 18 years. So this is a very expensive project. It was also criticized, but it's at the same time it's a high value project. There's a realistic chance to make this work. Would benefit not only today's generation but also future generations. That's why I think this is a very important project. This is the scheme of the coil system of Wendelstein 7X in blue, and plasma is shown in yellow. This is an experimental visualization of the field on a magnetic surface in Wendelstein 7X. The form and the position of the coil system was calculated using supercomputers, and Wendelstein 7X has its own data center for processing the data. This is a picture of Wendelstein 7X of the measurement of the coils. And this is a picture of a superconducting ring cyclotron. This is another application for superconductors. This is the radioactive isotope beam factory at the Riken Nishina Center for Accelerator-Based Science in Wako, Japan. The cyclotron is a particle accelerator. It was invented by Ernest O. Lawrence in 1929-1930 at the University of California in Berkeley. Today there are over 1,500 cyclotron facilities in the world. And they are used to make the radioactive isotopes for cancer diagnosis, for example, fluorine-18, and for cancer treatment. This is a nice movie of the Meissner-Ochsenfeld effect at a temperature below the critical temperature. The superconductor is cooled down with liquid nitrogen. So this is a high temperature superconductor. Once the temperature is below the critical temperature, the magnet will start to float. After a while, the liquid nitrogen will evaporate. The superconductor will get warmer, and the magnet comes back. That was today's video about the high temperature superconductors. Thank you for watching. Have a nice day. Bye bye.